Point the camera at Mars and hold your breath. The red planet hangs under the sun's glare, and something older than our maps is angling toward it. If intent can be read from motion, then tonight is a lie detector. They call it 3I Atlas, the third interstellar visitor ever confirmed. It is not captured by the sun. Its path is a stretched sling, an open curve that will never close, a hyperbola that writes itself across the ecliptic in cold fire. Far from the sun, its surplus speed is roughly 58 kilometers per second, a number that shrugs at gravity wells. Mars sits near the plane where this traveler cuts across. By geometry alone, the red world becomes a stage. By timing alone, the stage becomes a test. If the comet merely coasts, its track will match the equations. If outgassing thrust flutters, the track will twitch. If there is pattern beyond physics, the data will have to say it out loud. So we set up the instruments. From orbit around Mars, watchers can sweep the exosphere and read traces of water vapor, carbon dioxide, and faint carbon bands. From Earth, telescopes chase the shrinking elongation, teasing signal from daylight. Spectrographs listen for asymmetric breath. Radio arrays pin down the motion. The plan is simple and ruthless. Compare prediction to reality, and keep comparing. Midway through the run, the question sharpens like a blade. What does an interstellar comet want with Mars? The narrator steps back. No whispering prophecies, no hurried leaps. We will write this like a forensic ledger. First, we will state what the sky is doing. Next, we will test the simplest story, that nothing wants anything and geometry is enough. Then, if the numbers bend, we will follow the bend, wherever it leads. Call it what it is, an interstellar visitor. 3I Atlas is the third confirmed object from beyond the Sun's family. Discovered on the 1st of July 2025 by the Atlas survey in Chile, it did not form here. It is passing through, carrying the arithmetic of another sky. Interstellar means unbound, a one-time path through our streets of light. It will not stay. Its path is not a loop, but an open cut through the ecliptic. A hyperbolic orbit means the Sun cannot keep it. Far from the Sun, its surplus speed holds near 58 kilometers per second. The trajectory is retrograde, tilted 175 degrees to the planetary plane. It will reach closest to the Sun near the end of October at about 1.4 astronomical units, just inside the orbit of Mars. Unlike the first interstellar arrival in 2017, Oumuamua, this one looks and behaves like a comet. A faint, expanding coma wraps a nucleus we cannot yet see directly. Dust and gas stream into tails. Early spectra point to strong carbon dioxide, with water vapor turning on as sunlight grows harsher. Brightness blends dust, ice, and geometry, which means size is still a range, not a number. Albedo is a guess. Activity changes with time, angle, and distance. Compared with the second visitor, Borisov in 2019, 3I Atlas appears faster, with more volatile push shaping its breath. Yet the honest summary is uncertainty with boundaries. We measure an absolute brightness that wobbles with viewing angle. We assume a reflectivity and get a diameter that spans from a small mountain to a county. We fit a trajectory and ask whether non-gravitational nudges are present or not. This primer sets our rules of inference. Start the clock. The comet's path slices the plane of planets and grazes the orbit of Mars. No steering is required for this rendezvous. Geometry does the work, drawing a command across the sky. Observe now. In early October, the mist distance tightens to about 0.2 astronomical units, 29 million kilometers. Approach speed stays in the tens of kilometers per second, too fast for capture, fast enough that small forces can matter when integrated over weeks. Late October brings perihelion near 1.4 astronomical units. In early November, the track tilts past the Venus neighborhood. By mid-December, Earth is far, and the visitor is fading. Early next year, the deep reach toward Jupiter's domain continues. Here is the blade test, placed at Mars. If motion is only gravity, the plotted ephemeris will lock to reality. If asymmetric outgassing adds thrust, the track will flinch, a measurable millimeter in the right units, a telltale second on the clock. From Mars, the comet's apparent path crosses low elongations with the Sun, but grows a favorable phase angle. Dust tail points roughly away from the Sun. The ion tail kinks with the solar wind. Parallax between spacecraft can sharpen positions to exquisite precision. From Earth, shrinking elongation makes twilight hunts and daytime subtraction necessary. The red planet's orbiters keep their vigil while ground telescopes blink through glare. The advantage shifts to Mars. Why Mars? Because the retrograde, high-inclination orbit cuts the ecliptic near the radius of Mars, and the timing places the node here. It is not a target so much as a crossing. Practically, this yields a narrow window around closest approach, a schedule of rapid astrometry and brightness sampling. If nothing interesting happens, the numbers will behave. If something does, it will be here first. Call the red planet what it is, a laboratory with a moving roof and a clock on every wall. Here, geometry gives leverage. The phase angle grows. The solar elongation shrinks. Parallax between platforms turns tiny motions into measurable facts. Mars is not the target. Mars is the vantage. Start with the Mars atmosphere and volatile evolution mission. It tastes upper air, and the plasma wraps the planet. It can map how the solar wind drapes field lines and how an ion tail might thread that curtain. If the interstellar comet breathes unevenly, the charged exhaust will whisper in the data. Now the Mars Reconnaissance Orbiter, its cameras watch daylight glare and the dusty sky, building stable baselines for brightness. A tail that thickens or thins against the background can be tracked hour by hour. When geometry forces low elongations, consistency matters more than depth. This spacecraft is a metronome. Bring in the ExoMars Trace Gas Orbiter. It hunts faint molecules, water vapor, carbon dioxide, carbon chains and odd cousins that light up in ultraviolet and infrared bands. A skewed line shape or a shifted ratio across time is a clue to thrust, not just sunlight. Add the Emirates Mars mission. Wide-field imaging and thermal eyes sketch the global scene. Dust storms, high clouds, aurora, like veils. These change the contrast and the scattering that our other instruments must fight through. Context prevents costly false positives. All teams sync their clocks. Intervals tighten around closest approach. Astrometry from Mars triangulates with Earth-based telescopes. We turn motion into a ledger. Position, brightness, spectrum, again and again. If the sky has nothing to hide, every column will balance. If it does, the first imbalance will show here. What experiment is the heavens running, and what is it trying to conceal? State the simplest story first. The interstellar comet is just passing through. Gravity writes the line, and the line holds. No intent, no steering, no message. If this null hypothesis is true, every measured point will fall where the equations say it should, inside uncertainties from noise and glare. What would we expect to see? A coma that is symmetric about the sunward line. A dust tail that opens and fades with distance from the sun. An ion tail that bends with the solar wind but shows no thrusting jet. Brightness that rises and falls gently with phase angle and sunlight, not as spasms. Position residuals scattered like fair dice around zero. How do we check? Cross-tied astrometry from Mars orbit and Earth, with times on the same metronome. Fit a gravitational solution, then allow a tiny non-gravitational term and ask whether it matters. Read spectra for water vapor, carbon dioxide and carbon bands. Test for stable line shapes and balance blue to red ratios. Use the Venus neighborhood pass in early November as a control. Use the long glide toward the Jupiter region early next year as a second control. Calibrate and repeat. Is it safe? The mist distance at Mars is on the order of 1/5 of an astronomical unit. Dust density at that range is thin as breath. Risks to orbiters and surface assets are negligible. Earth is nowhere near harm. Where does the hypothesis break? When position residuals pull beyond the budget repeatedly, when the brightness curve shows time-locked kinks, when spectral asymmetries repeat across nights, when a single non-gravitational parameter explains the entire season better than gravity alone. If the null story survives, the mystery shrinks. If it breaks, we will be forced to read intent from the smallest differences. Begin with the cleanest move, a gravity play. No jets, no technology, no hidden thrusts. The comet skims the planetary plane, and Mars drifts near the crossing. Can gravity alone, at this distance, bend the path in any useful way? Closest approach is near 1/5 of an astronomical unit, about 29 million kilometers. Mars is small compared with the Sun and with Jupiter. At that range, its tug is tens of thousands of times weaker than the Sun's. The path speed is in the tens of kilometers per second. A gentle pull over days integrates into a whisper, not a turn. Mars's hill sphere, the rough boundary of efficient influence, spans about 1 million kilometers. The mist distance is many tens of hill radii. Slingshots live near the shoulder. Far outside, geometry wins and leverage dies. Midway check. If gravity alone is the hand on the wheel, the curve will not betray a touch. So the expectation is ordinary. A multi-body gravitational solution fits the data without help from non-gravitational terms. Position residuals center on zero and spread like fair noise. The coma stays balanced about the sunward line. The dust tail opens with phase. The ion tail bows to the solar wind without a steady kink. How to test it? Fit 2 families of solutions, one with Mars's tug emphasized, one with it muted. Set a detection threshold at a few milliseconds and repeat night after night from Mars' orbit and from Earth. If the 2 families are observationally indistinguishable, the gravity play explains the season. If a single tiny nudge term cleans the table better than gravity alone, the play fails. And then the question sharpens. If Mars cannot steer at this range, what could? The breath of the comet may try. Watch closely. If gravity cannot steer, breath can. Comets breathe, and when they exhale unevenly, they push. 3I Atlas approaches the Sun, warms on one side and ice turns to gas. Dust rides the flow. The push is tiny. Over days, the push adds up, a steady hand on a wheel you barely feel until the road drifts. The physics is simple and sneaky. At 1.4 astronomical units, carbon dioxide wakes early. Water vapor follows as heat soaks deeper. Rotation brings hot noon after the subsolar point moved on. That thermal lag turns vertical lift into a sideways shove. One hemisphere dominates. A jet, weak or strong, becomes a rudder. What would show in the sky? A coma with a lopsided glow, a dust tail that opens unevenly across the phase angle, an ion tail that kinks in the solar wind out there but remembers the jet. Night after night, the brightness curve would not simply rise and fall, it would pulse with a steady, repeatable clock. Spectra would whisper direction. Water bands and carbon dioxide lines would change in balance, skew blue or red as gas prefers one heading. Cyanogen and diatomic carbon, classic tracers, would flare on the side that faces the wind. Line shapes would fatten. Ratios would shift with rotation. The motion would tattle too. Position residuals would carry a period, matching the comet's day. A non-gravitational term would improve the fit in radial, transverse, or normal directions. Small, steady, cumulative. From Mars orbit, parallax would amplify the difference between models with breath and models without. So we run the paired tests. Predict with gravity alone, predict with a small shove. Overlay the sky. If breath is the helm, the curve will bend first over Mars. Then comes the harder question. Toward what waypoint? Treat the idea with gloves on. Reconnaissance is intent, not accident. It means choosing a vantage and collecting information. The scientific default says 3I Atlas is natural. Any claim of technology demands evidence that is clear and repeated beyond mundane physics. Mars offers advantages a machine would notice. The planet sits near the solar plane. It carries a lattice of orbiters that relay radio and whisper plasma data. Lines of sight skim the solar corona, a region that modulates signals like a filter. It is an ideal perch. What would the sky show if reconnaissance were real? A coma whose brightest sector sweeps like a beam with a cadence that does not match the comet's day. A dust fan that keeps a strange alignment when geometry says it should roll. An ion tail that points not only away from the Sun, but also persistently toward the Mars direction. In instruments, we would look for narrow radio tones that wake only when Mars is in the path. We would test for unusual polarization in optical or ultraviolet bands. We would measure timing offsets as signals cross the corona, hunting for a deliberate pattern. Dynamics would carry fingerprints too. Non-gravitational parameters would wobble with the Sun-Mars comet geometry instead of with simple heating. A favored bearing would be held for hours beyond what thermal lag permits. But nature has many disguises. Rotating jets can mimic beams. Solar wind gusts kink ion tails. Dust storms over Mars alter backgrounds. Instruments lie when dazzled, so we design a harsh test. Synchronize Mars orbiters with Earth-based radio arrays. Correlate brightness, spectrum, tail vectors, and geometry. Demand repeatability across nights. If the light is only heat, patterns will obey thermodynamics. If not, why does the sweep peak when Mars faces the window begin with a different instinct? Seeds, not targets. The narrator considers 3i Atlas not as a hunter, but as a carrier. In that frame, Mars is a passerby on the shoulder of a long road, not a destination. The value is not geometry, the value is cargo. Interstellar comets shed dust and gas that predate our sun. Carbon dioxide wakes early, water follows, and carbon chains unravel into spectral hints of chemistry older than home. Grain by grain, a plume of micron-sized particles leaks into the solar wind and joins the zodiacal cloud. Most grains sail past everything, a few fall behind. Fewer still drift near Mars. The probability of delivery is tiny, but the ledger of space is written over epochs, not nights. What would count as proof of seeds? Isotopes that do not match local norms, a deuterium to hydrogen ratio that sits outside the spread of solar comets, carbon-13 to carbon-12 that shifts the line, nitrogen-15 to nitrogen-14 that argues for a colder nursery, color slopes that run redder or bluer than our catalogue, polarization curves that betray different grain shapes, a size distribution skewed toward fragile, fluffy aggregates built in faint starlight. The test is patient and careful. Trace gas spectrometers chase weak bands while imagers track dust brightness against changing phase. Models subtract geometry and leave material fingerprints. Mars helps by offering vantage, not because it is being aimed at, but because the crossing happens there. Occam's razor stays on the table. Thermal activity and changing wind can mimic novelty. If the spectra and isotopes fall inside the ordinary range, the interstellar story shrinks. If they do not, the simplest reading remains. 3i Atlas is not seeking Mars at all, it is spilling a faraway dawn out here. Write the prediction before you touch the data. That is the rule. State the numbers, the tolerances, the places where the story must break. Then pick up the instruments and see whether the sky agrees. If it does not, change the story. Astrometry first. Compute a multibody gravitational ephemeris and set uncertainty bands. Measure positions from Mars orbit and from Earth. Subtract prediction from reality. If residuals wander without pattern, the null story holds. If they drift with a period or a bearing, it breaks. Photometry next. Build a brightness curve across phase angle. Expect smooth change, no steps. Repeated pulses that survive background corrections argue for hidden thrust or missing geometry. Now spectroscopy. Track water vapor, carbon dioxide, cyanogen, and diatomic carbon. Watch line shapes and the balance between blue and red wings. Stable, symmetric lines point to passive heating. A steady skew that maps to a preferred heading strengthens the outgassing helm. Tail morphology adds vectors. The dust fan should open with phase and point away from the sun. The ion tail should bow with the solar wind. A persistent lean toward the Mars direction is a red flag for reconnaissance. Interplanetary parallax ties it together. Triangulate Mars and Earth to tighten range and direction. Disagreement after careful calibration means our force model is wrong. Fix it or admit a new term. Keep the statistics honest. Pre-register tests. Demand repetition across nights. Decision tree, simple and firm. If gravity alone fits, keep the null or the gravity play. If a small, stable shove is required, the outgassing helm wins. If geometry with Mars appears in the timing, consider reconnaissance. If composition stands outside local norms, the seed story strengthens. If the numbers refuse to lie, we follow them. We follow them to Mars and beyond tonight, set the stage and count the instruments. The window around closest approach is short, and the plan is ruthless. Position, brightness, spectrum, tail vectors, again from Mars and from Earth. Begin with Mars' atmosphere and volatile evolution. It rides the upper air and tastes the plasma that wraps the planet. Its ultraviolet imager reads the glow of hydrogen and oxygen. Its solar wind analyzer and ion sensors watch how charged particles flow. Its magnetometers map drape of fields. If an interstellar ion tail threads this curtain, the pattern will change. Next, Mars Reconnaissance Orbiter. The high-resolution imaging science experiment, the context camera, and the Mars Color Imager give stable baselines in daylight glare. They track brightness hour by hour, measure the shape of the dust fan, and flag sudden changes that do not match weather. Then the ExoMars Trace Gas Orbiter, the nadir and occultation for Mars Discovery Spectrometer, and the Atmospheric Chemistry Suite split light with patience. They chase water vapor, carbon dioxide, cyanogen, and diatomic carbon. Line shapes, wing asymmetries, and tiny Doppler shifts speak to motion and direction. Add the Emirates Mars mission. The Emirates Exploration Imager, the Emirates Mars Infrared Spectrometer, and the Emirates Ultraviolet Spectrometer sketch the global stage. Dust, high clouds, aurora, and temperature fields. Context rescues interpretation. Tie it to Earth. Ground telescopes and radio arrays provide a second angle. Deep space antennas time occultations across the solar corona. Parallax locks distance. Disagreement after calibration forces a better model. Operations matter. Sun avoidance angles. Planet-wide dust storms. Data rates and downlink windows, radiation spikes. A simple rule runs beneath the complexity. Synchronize clocks, tighten intervals, and protect the assets. When every watch is in step, the smallest deflection will stand alone. Is it noise or the finger of an unseen helm? On Earth, the windows are narrow and bright. Around perihelion, the comet hovers close to the sun in the sky, and geometry becomes a lock that light itself keeps. Observers must work at the edge of day, where contrast is poor. Define the scene. Solar elongation drops to small angles. The object rides low, often within the glare of the zodiacal band. Safe practice demands a minimum sun altitude and mechanical limits that protect optics. A twilight window opens before sunrise and after sunset. It moves with latitude and weather. Miss the window and you lose the night. Strategy for optical work. Track the object, not the stars. Use short and medium exposures in brackets. Employ narrowband filters to cut sky glow and isolate emission from water, carbon dioxide, cyanogen, and diatomic carbon. Baffle the horizon with boards or domes. Keep reference stars in frame for calibration when possible. Geometry complicates brightness. Phase angle and scattering change the apparent flux more than activity does. Build a predicted phase curve, then correct for atmospheric extinction and for zodiacal dust. Subtract those first. Only then ask whether the comet itself changed. Daylight attempts demand extra caution. Use coronagraphs and careful baffling. Subtract a moving background model. Respect safety margins for the sun. Know when to stop. Radio offers different leverage. Radar is useless at these distances, but interplanetary scintillation can diagnose plasma structure. Deep space antennas can time occultations across the solar corona and test polarization changes. These are delicate measurements, but the sky sometimes rewards patience. Now sync to Mars, lock timestamps, triangulate distance and direction, share pre-processed products both ways. In a narrow season, coordination is the only multiplier. If Earth can only see what light permits, where will the rest show, and when must we refuse to blink? Begin with the calmest sentence in the book: there is no collision risk. The interstellar comet will miss Mars by about 0.2 astronomical units, a gulf of 30 million kilometers. At that range, the nucleus is a whisper. The danger to spacecraft and rovers is not impact, it is environment, dust, plasma, glare, and operations. Dust first. Particle density at that distance is extremely low. Relative speed is high, but cross-section is tiny and shielding is proven. the probability of a destructive hit is vanishingly small. Spacecraft can enter safe configurations during peak dust forecasts and still resume observations within minutes. Next, ion tail and plasma. Mars lives inside a draped magnetic sheath. Uneven outgassing can feed a slim ribbon of ions into that sheath and raise charging noise. Mars' atmosphere and volatile evolution is the early warning. If the plasma turns lively, teams pause sensitive modes, ride out the gust, and restart. Now optical and thermal stress. Small solar elongations mean glare. Cameras shorten exposures, narrow filters, and respect sun avoidance angles. Radiators and heaters keep temperatures inside the green band. If margins shrink, cadence slows, and duty cycles lighten. Surface assets are insulated by chance. At these distances, cometary grains almost never fall on Mars. Planetary weather, not comet weather, dominates their day. Operators plan conservatively to avoid mistaking local dust for comet signals. Operations tie the knot. Deep space antennas schedule daylight passes around the sun. Data rates and downlink windows are rationed. Radiation alerts sit on dashboards. A simple rule governs all of it: protect the assets, then harvest the data. The closing hook is simple, too. When physical risk is low, the only real danger is interpretive. A tiny, systematic error can forge a false mystery. The cure is discipline and repetition. Lay every layer on a single timeline. Positions from Mars and from Earth. Residuals night by night. Brightness curves across changing phase. Spectra that breathe or do not. Tail vectors that listen to the solar wind. Place each point where it belongs, then ask what refuses to belong. Now build a matrix. Hypotheses down the rows, signals across the columns. Null, gravity play, outgassing helm, reconnaissance sweep, seeds from another nursery. Score what raises their odds and what cuts them down. Use simple Bayes in plain language. Prior belief, likelihood from the data, updated belief at dawn. Define intent with care. Intent is not drama. Intent is a stable preference in motion that survives geometry and weather. It holds a bearing longer than thermal lag allows. It locks a cadence to the Sun-Mars comet layout, not to the comet's day. It repeats when the window opens. 4 consistent endings emerge. First, everything fits gravity within error. The case closes. Second, a small, steady, non-gravitational push improves every fit. The helm is breath. Third, a sweep appears that times itself to Mars geometry and not to heating. That is the recon alarm, and it requires brutal confirmation. Fourth, composition and isotopes land outside local ranges. Seeds win on substance, not on aim. Guard against mirages. Do not polish noise into signals. Pre-register the tests. Control for many comparisons. Blind cross-checks between Mars platforms and Earth teams. Prefer missed miracles to false ones. Decision rules follow. Declare no intent when patterns die under repetition. Elevate the outgassing helm when one push parameter rules nights. Flag recon only after the pattern outlives 3 windows. Confirm seeds when composition departs far beyond the catalog with independent instruments across multiple nights. If motion is a signed statement, which script is it signing now? Begin with a verdict. The measurements point to a simple answer. Geometry rules. Breath assists. Intention does not. 3i Atlas passes Mars because the crossing lives there, not because the comet seeks it. The confidence is cautious and earned by repetition. Yet endings deserve branches. If gravity alone had ruled, we would have said the story ends in silence. If a small, steady shove improves every fit, we keep the outgassing helm and call it mundane. If a sweep had timed itself to Mars windows, we would have raised a reconnaissance alarm and demanded brutal proof. If composition had sat far beyond local catalogues, we would have crowned the seed story. If signals refused to repeat, we would have filed it as not concluded. Mars taught us vantage, phase angle, parallax, and context turn raw light into knowledge. Near Mars, the sky made our tools honest. Far from Mars, the same discipline still applies. Limits remain, noise is patient, backgrounds lie, overfitting flatters. We accept non-evidence and publish thresholds carefully before we cross them. The cure for glamour is replication. Practical effects matter. Future alerts will pair planets and Earth whenever geometry grants leverage. Interstellar hunters will budget for cross-world timing, parallax, and pipelines. Campaigns will protect assets first, then chase faint claims. Next steps are plain. Track the object as it fades. Refit the trajectory with the full arc. Watch the brightness curve relax. Check whether spectral balance is quiet. Close the file when the last prediction and the last point shake hands. Now the private layer. Humans read will where nature writes motion. That is our risk and our gift. If the numbers change tomorrow night, we will change the answer. What does the comet want with Mars? It wants us to learn how to listen.